Hello everybody and welcome back to Python for Aerospace. In today's lesson we're going to calculate the lift and drag coefficient around our NACA Airfoil 4418. We're gonna do this for two different Reynolds numbers, and we're gonna have also a quick overview about what the Reynolds number is. And after that we're gonna start coding. So let's get started.
That's one small step for man, one giant leap for mankind.
So, as I just said, we're going to have a quick introduction about the Reynolds number, which is defined right here in the middle. It can be interpreted as the ratio between two forces. Especially we have on the numerator the inertial forces and the denominator the viscous forces. And this number is quite useful to understand whether the flow is laminar or turbulent. The higher the Reynolds number, the more likely the flow is turbulent. Of course, here in our topic today, we want to calculate lift and the drag coefficient. The drag coefficient makes sense only in the case where we have a viscous flows. Otherwise, there's no drag at all. So we can start coding. So the first thing we need to do is to install the XFoil library, which will allow us to calculate the aerodynamic coefficients around the airfoil. So you guys have here the link to the page where you can download the XFoil package. Otherwise, yeah, you can either download it directly from here, from GitHub, or you can type this line of code into the terminal and it should install it into your environment. So I already have done that, and if you don't know how to do it, maybe you can write it below in the comments and I will show you how to install packages in Python if you don't know how to do it. So after installation, we can start by importing the library XFoil. So from XFoil import capital F, X, and F foil. Good, it's working. Now from here we need to create an instance of the class XFoil, right? Of class, and we're gonna call it XF equals to XFoil. Let's run it. There's a mistake here. There's always a capital F, which I forget. Yes, now it's working. Good. What we need to do now is we need to pass to the class the information about the geometry of the airfoil that we have created in the previous lesson, right? Because right now this object here doesn't know about anything about this airfoil. So this is very simple, and we can add the information about the geometry. So we need just to type add information about the airfoil geometry, and here we're going to have xf.airfoil equals to NACA 4418. Yes, looks like so far no mistakes. Good. Let's start by doing the simplest case ever, where we don't have at the beginning any viscosity. So the Reynolds number is not gonna be present, okay, in our simulation. Let's forget about the Reynolds number to begin with. We need to add a maximum number of iterations that the algorithm must perform. And we can do this in order to solve the equations, of course. So we can do this by telling the max number of iterations, okay? And we can do this by typing xf.maxiter, and we're going to set it to 40, for example. And now we can run the simulation to calculate lift, drag, which doesn't make sense in this case, momentum and pressure and coefficients, yeah, pressure coefficients. And then the line of code to this is the following. So we're going to have A, which is the array containing all the angles of attack through which we are going to iterate in order to calculate our coefficients, because the aerodynamic coefficients are not just like one, but they have they're a range and they depend on the angle of attack, which again, if you don't remember, is basically the angle between the chord line and the relative wind. Okay, so yeah, so we have this array of angles, then we have the lift coefficient, the drag coefficient, a momentum coefficient, and pressure coefficient. And in order to calculate, we need to call the object XF and call this function ASEQ. And the inputs of this function are going to be the minimum and the maximum angle of attack and the step at which we discretize the range of the angles. So the minimum alpha angle, then we have the maximum alpha, and then the step, right? So we need to define also these variables. Let's do it here, and we call it define angles of attack. Okay, so we can do, for example, minimum alpha equals minus 16 degrees, max alpha equals to plus 16, and the step for alpha is equals to, I don't know, 0.5 degrees. Okay, we are set, and let's try to run the code. All right, good. So the code is not crashing. Looks like let's check if we have some results in here. Let me add one cell here. Let's try. So let's see the range of angles. Good. They go from minus 16 to 15.5, which is okay. Then we have, let's see, the lift coefficient. Boom. Here we got our lift coefficient. Now we said that the drag should be all zeros. And yes, that makes sense. The moment coefficient, I think it's called moment in English. I'm not sure now. Let me check. I will check 1 second. Yeah, I think it's called pitch and moment coefficient, but you know what I'm talking about. And then we have the pressure coefficient around the airfoil. Good, nice. Let's now, we could create some plots to see what all of this looks like, right? But before that, we need to modify the definition of the unit chord, because right now we have n coordinates, okay, and this number basically is equal both for the upper and the lower part of the airfoil. So if I set, for example, 300, I have 300 points in the upper and 300 points in the lower part of the airfoil. And this is a bit misleading in my opinion, I think if we define as number of coordinates equal 300, we should have 300 points all over the airfoil. And this is, I think, useful for us because it will speed up a bit the computation of the coefficients. So let's go back here in our function, and we can divide the number of coordinates by 2. So if we set 300, it would be 300 overall the airfoil. Good. Now let's run for real our function, and it looks like it's working correctly. Let's check the outputs and see if they make sense. So here we have the angles of attacks, which are correct. Then we have the lift coefficient, which is also looking right. Then the drag coefficient should be 0. Yes, as expected. And the pitching moment coefficient, yeah, is different from 0. And finally, we have the pressure coefficient also looking good. What we can do now is to add a function to, or not a function, but some lines of code to display the aerodynamics coefficients, and let's do that. So we can start by plotting the lift coefficient, and therefore we need to create a figure, for example, like this, and we can define the size of the figure. Fixed size equals to, let's do 12.9. This case, I like that. Then we can plot the angles of attack versus the lift coefficient. It's gonna be a blue line, and we're gonna label it as CL, and this is gonna be displayed in the legend. We can call it legend, so it is displayed in the figure, and we can label also the x and y axis. So plt.x label, and here we have alpha in degrees. Oops. And then we have plot y label equals to CL and no units. Finally, we have the title. The title is going to be what? Lift coefficient over alpha, and in order to display alpha in a string, we can use the following code that you can find on Google, and then we have the NACA Airfoil series, right? NACA 4418 series. To conclude, we can display the image. Let's show it. So here we have a mistake. It says PLT. Yeah, there's an O missing here. Yeah, and this is good. We have, it's a linear shape. We don't have any stalling at any of the angles of attack, and this is because there is no viscosity, and therefore the airflow will always be attached to the surfaces of the airfoil, which is correct. Now we can copy paste this and also display the drag coefficient. So here we have drag, here lift coefficient. So CD. Here we're gonna have CD and CD, and it should be like a flat line. And here we have moment coefficient CM. Here CM. Good. So let's show the results. Nice. CM is all 0, and this is the lift coefficient. Successful. As we specified at the beginning, we would like also to test all this code with at different Reynolds numbers. So in order to do that, let's define the Reynolds number. And we can do that very simple. So we can do xf dot re, oops, sorry, here add information about Reynolds if Viscous. Okay, so if we can do xf.re equals to the Reynolds number, and for now it's 600,000. So okay, and actually we can incorporate this in our code, and let's see. It will take a few seconds to elaborate all the calculations, so let's wait for it. Very good. So we can see that our code is working more or less correctly. In some cases here I was not able to compute the lift coefficient or the drag coefficient, but anyways, I think we start to have some pretty good results. I think we can improve this by increasing the number of points over the geometry. Yeah, let's do 400 here. Okay, and let's run again the whole code and wait for a few seconds. Okay, and yeah, we can see that the gaps have reduced. So I assume that if we still increase the number of points defining our geometry, we will be able to fill up these gaps as well. Good. What do we do next? We can include these lines of code into our class actually. So let's try to do that. This should be quite simple, as we just need to define the method, and we can call it calculate coefficients. And as input, okay, is always going to have self, which contains the information about the geometry of the airfoil. And then we're going to have alpha min, then alpha max, and I would say also, yeah, of course, alpha step, and finally the Reynolds number. Okay, so the lines of code are actually pretty easy to add because we have it already here. So let's do it like this. Yeah, we can bring this up here and copy it. Let's make sure that all the tabs are correct. And we can move the package up here. Nice. Why do we write also the Reynolds number as an input variable? It's because we can, in such a way, we can distinguish between the viscous and non-viscous flow. So if we set, for example, Reynolds number equal to none, it means that we're not going to use any Reynolds number. And here we can set that if Reynolds number is given, then the Reynolds number that we need to store into our object is equal to the input one. If it's not given, like in this case, this statement will be skipped, and we're gonna just have the non-viscous scenario. So add information about viscosity. Or actually about Reynolds if viscous. Yeah. Now I like it more, and this can be removed, right? Because it's part of our inputs. And what does our function return? Well, what we could do is we could create a dictionary that stores all the different scenarios that we test for the same geometry. So if we have this geometry here, okay, and we want to test the different scenarios at different Reynolds numbers, at different angles of attacks, and so on, we don't need to store all the outputs in different variables, but we could create like a dictionary where we store all the variables for each scenario. So let's do that, right? We can write down store coefficients for new configuration, right? And how do we do that? Well, we need this dictionary, right? Where to store the variable. But yeah, so how can we define it? So a dictionary is defined like this. So we're gonna have a colon, which is kind of like equal to what? To a. So if from the dictionary we access the key a, we're gonna get all the angles of attack. And same for the rest of the variables. So CL is gonna be equal to CL, CD, oops, where am I? Let's go back here. CD is equals to CD, CM is equals to CM, and finally CP is equals to CP. All right, so we define the dictionary and we need to store this where? Well, we could store each dictionary into what? Yeah, into another dictionary. And this dictionary will have as a main key what? The configuration parameters. So basically the minimum and maximum angle of attack, the step of the angle of attack, and the Reynolds number. So let's do that. We can say that our coefficient dictionary is equal to this when, well, here we need to define the key, right? That is going to store the variables. So we can use, we can convert the alpha as a string to which we append another string in this way. So we're going to have the minimum angle of attack, the maximum angle of attack, then underscore what? The step. So plus the alpha step, and finally underscore the Reynolds number, right? Yes. But we want this dictionary to be part of the object. So how do we do that? Then we can create here in self, we can create the dictionary as an empty one. And every time we call this method, we are going to generate a new key, which is this one. And if we call this key, we're going to have all the variables of the new scenario. Or let me explain better. We're going to have all the aerodynamic coefficients for such a scenario. So yeah, it looks good to me now. Let's check for some mistakes. Invalid syntax. Somewhere we have a mistake. Let's investigate. Yeah, the mistake is right here. I have an extra bracket which shouldn't be there. And now, yes, the code is working properly. So how do we run now the method that we just created? It's very simple. We call our object, and from here we call the method. And the method is called calculate coefficients. So let's copy this. And let's set it here. Self doesn't need to be used anymore as an input because the information is performed here. Actually, here it should be self, and that's it, because self contains already all the information of the geometry, as you can see here. So let's generate again, and let's try to run the code one more time. Yeah, alpha main is not defined for sure. Let's set -16 plus 16. The step is 0.5 and no Reynolds number. Okay, let's wait a few seconds to calculate the coefficients. So Python is done calculating, and let's check which attributes we have in our object. And we can see that we have a variable called coef dictionary. Let's look inside of it. It looks good to me, as a matter of fact, or actually not so good. No, it doesn't look good to me, as yeah, here the drag coefficient is not 0. So let's check why that is wrong. Yeah, the mistake is here. These lines of code is overwritten, so it needs to be removed. So let's run again, and yeah, now we can see that the drag coefficient is 0 as expected. Nice. So NACA 4418.coef dict is a dictionary where if you call this key here, which contains basically the scenario that you're testing, you can find another dictionary inside where all the aerodynamic coefficients are stored. So for example, we could access it very easily by calling the first key, which is this one, yeah, and then we can access again, for example, the lift coefficient, CL, and there we have it, right? This is quite good, because now we can do multiple things. For example, we could create new scenarios, for example, where the angle of attack is changed, or not only the angle of attack, but we can test also different Reynolds number. For example, here we can have 200,000 and here 600,000. And now we're gonna run it, and then we're gonna try to compare the results. So let's do that. In order to plot the coefficients, we could reuse the function that we wrote down here, right? But we can also include this line of code into another method of our NACA class. So, and this will be helpful because it will simplify the way we can plot the coefficients. And let's see how we can do this. So we can define the method called plot coefficients, and as input. Of course, we're going to have a self and the configuration, right? Configuration, perfect. Now let's extract from the configuration, which is a string and actually corresponds to what we defined up here. Let's extract the quantities that we are interested in. So we can define extract coefficients information info. Perfect. And we can do config is equal to what? To self dot coefdict, right? And then from here we're gonna have what? The configuration. So we are basically setting this key to extract all the aerodynamic coefficients from the dictionary. And then we can have A, the angles of attack, equals to config A, so we are accessing the key A, and the same can be done for all the other quantities. So it can be done for the lift coefficient, the drag, momentum, and the pressure coefficient. So again, even here we need to change the keys of the dictionaries, and we are good. And now what we can do is we can copy these lines of code, and we can move it up here. So let's make sure all the indentations are correct. And it looks like to me that we are good. So we have a lift, drag, and momentum. And yeah, I believe we can run this function. Yes, so here let's run the code again. Yeah, so we can now run the new method that we just created. So let's test it with the easiest case. So plot coefficients, and as a configuration, let's do -20 to 20, step 0.5, and none as Reynolds number. Boom. Yeah, looks like it's correct. Let's try with a different Reynolds number, 200,000. And yes, we got something. And with 600,000, yes, we get the results. Awesome. So we can have all these plots all together here. And I believe we reached our goal of displaying the different aerodynamic coefficients at different configurations. So I think it's mission accomplished so far. We stored all the information inside of a dictionary, which is unique for this object. And I believe what we are left now is with the last step, which is to compare the calculated aerodynamic coefficients with experimental data. And we're going to see this in the next lecture, and I will show you how to capture the experimental data from a PDF file and import it here to overlap it to the graph that we just generated. So yeah, we're at the end of this lesson. Thank you for watching, and I hope to see you in the next video.